This lesson is going to be about healthy bone. In the beginning, I'm going to explore what bones are, sort of the gross anatomy, the different types of bones, explore long bones in detail, and then go through the histology of what an osteon is, and conclude the first beginning of this lesson with the steps of mineralization. That stuff's not really very important, but if you understand all those things, what comes next, the back half of this lesson, the interactions of osteoblasts and osteoclasts, and the pathologies that follow in the subsequent lessons, if you have a solid understanding of that anatomy and histology, becomes much easier to communicate. There's a lot of details, though, and it takes a long time to explain. And it's much better explained with illustrations and real examples. So in the beginning here, what I'm going to do is just catalog some of the high yield points, but actually constantly go out to either an illustration or example of real bone. The second thing is the way things are named. There is a scientist or a group of scientists who were really good at naming molecules based on what they did, but they had no idea what marketing or branding was. So they teamed up with someone who was really good at branding. The problem with that is that when someone doesn't know the subject material very well, you hear them say the wrong thing. I'm going to make it so that you say the right thing. First, bone is made of calcium phosphate crystals. It's called hydroxyapatite. Not like your hunger, it's spelled a little different, but hydroxyapatite. Then we're going to explore a lot the utility of rank ligand, and NF-kappa B. Rank, the receptor for activated nuclear factor kappa B, and rank-L, the rank ligand. Rank ligand activates rank. Rank uses NF-kappa B as a second messenger system. NF-kappa B stands for nuclear factor kappa light chain enhancer of activated B cells. NF-kappa B is the second messenger for rank, which is the receptor for rank ligand. And with that, let's begin the initial anatomy, histology, and vascular supply of bone. This is normal bone, and we're going to demonstrate this better than I can on the whiteboard, and I'll catalog the high yield stuff here. Normal bone. First, the types of bone. Bone can be categorized as a long bone, as in your extremities, humerus, femur. Short bones, like your hands and feet, metatarsals and phalanges. Flat bones, like your sternum and most of the bones of the skull, and what I called weird ones, like the vertebrae and the sphenoid. Let's take a look at some different types of bone. All bones are bone. It's logically the same. But the gross anatomy shape some of them take allow us to categorize them. Short bones, long bones, flat bones, irregular bones, and the patella. It's not very many short bones. They're usually found in the hand and the feet, the carpals and the tarsals. The flat bones are the sternum, the scapula, and most of the bones of the skull. When someone says a human bone, most people conjure the image of the dog chewing on the femur, and the femur is indeed a long bone. But there's many long bones in the human skeleton. Femur, tibia, fibula, humerus, radius, ulna, and even though they're small, they're still long bones, the metacarpals, metatarsals, and phalanges. And then there's a few weird ones, like the pelvis, vertebra, or the sphenoid bone. All right, so let's do a little bit deeper dive into long bones. This is where they get complicated. Long bones have ends, stylistically represented like a dog bone, and more accurately represented on the bottom. The long shaft in between the two ends is called the diaphysis. The very end, the little nubs, are called the epiphysis. There is an epiphyseal line where the growth plate fused. Above that line, but not yet diaphysis, is the metaphysis. In the diaphysis, you're going to have cortical bone all the way around a cylindrical shaft. In the middle is the medullary canal. This is where the bone marrow and blood vessels are. Cortical bone protects the bone marrow and is lined by bone lining cells. This is cortical bone. On the outside, facing the world, is the periosteum. Periosteum is a simple epithelium of bone lining cells. Wherever a cortical bone touches bone marrow, it is called the endosteum. In the metaphysis epiphysis area, you're going to get a similar arrangement, bone intermixed with bone marrow. Only trabecular bone is more haphazard. There's going to be spicules of bone where bone is, and wherever bone is not, is going to be bone marrow. This doesn't have a nice outer cortex, inner medulla feel to it. And whenever bone is going to articulate with a joint, it is going to be lined by chondrocytes, cartilage. All right, let's take a look at a deorganified bone. All bones are made of bone, but on a gross anatomy level, you can actually identify different orientations of bone. This is a femur, and you can see here in the diaphysis, in the shaft, there is thick cortical bone. And on the inside, in the medullary canal, is nothing. Now, of course, we can see the back of the bone, but that's cortical bone behind it. This is the cortical bone to the left. This is cortical bone to the right. And in here would normally be bone marrow and blood vessels. As you get up towards the metaphysis and the epiphysis, what you see is a transition from this medullary canal, which you can see on this other femur over here. The canal is this big circle spot, and this is all cortical bone all the way around. What you see is that the bone turns into trabecular bone, or also called spongy bone. Trabecular is preferred since bone isn't spongy, it's hard. So cortical bones, the thickness of the cortical bone sort of disappears and is replaced only by trabecular bone. Wherever there wasn't cortical bone down in the diaphysis, there was blood vessels and bone marrow. Up here in trabecular bone, if this had not been deorganified, it'd be the same case. Wherever there isn't trabecular bone, there are blood vessels or bone marrow. And not shown here because this is a fossil and the cartilage is lost. Wherever a bone is going to articulate with a joint, there would be a cap of cartilage. This is a long bone, and if you come over here and take a look at this vertebra from the outside, you can see that it's made of bone. And if you shaved it, cross-sectioned it, what you'd see is a similar arrangement. Cortical bone all the way around, cortical bone on the edge, and then this meshwork. This is all trabecular bone. The bone marrow has been removed, so all you see what's left behind is this mesh of trabecular bone. Cortical bone on the outside, trabecular bone on the inside. Long bones are special in that they have a medullary canal in the shaft where bone marrow and blood vessels are. Communicating histology of bone takes a long time, and so what I'm going to do is just go out to the illustration, talk over it, and when you come back, there's going to be stuff on the board that sort of is like the super highlights. All right, so here we're looking at decalcified bone. All the pink stuff is osteoid. This is a developing bone. That doesn't really matter for what I want to talk about, but on the outside here you can see sort of white nothingness. This is going to be mesenchyme of a developing bone. Pink stuff, osteoid. Bone lining cells separate all of the pink stuff from the outside, and that bone lining cells are on the other side as well. We'll get a closer look in just a second. You can definitely see that there are circular-ish structures. Those are osteons. There's definitely space in between them, of the interstitial lamellae. And then there are these white spaces with little purple dots in them. The big white spaces in the middle of each osteon would be where the blood vessel would be that serves that osteon. The other little white spaces are the lacunae, artifacts of preparation where the osteocytes are. If we zoom in a little closer, we can see some of the details. This osteonal canal is lined by bone lining cells. This osteonal canal lined by bone lining cells, separating the pink stuff from something else, just as the bone lining cells on the outside did on the previous slide. This actually is an interesting shot because you can see here this osteonal artery is going to have concentric rings of cells, lamellae, around it, and as you reach its outer layer, you can see it almost cuts this osteonal artery off. Right? So this osteon is newer and had bored its way through a pre-existing osteon based on this osteonal canal. These are going to become interstitial lamellae, where these are the new fresh ones. These white spaces are called lacunae, or singular lacuna, where the osteocyte lives. In living tissue, there's no space. The osteocyte is completely encased in osteoid that has been mineralized, that is calcified to become bony matrix. Down here, because this is immature developing bone, I don't want to get hung up on this in this lesson, but here you can see that there are no concentric rings. This is woven bone. Don't focus on this. I want to keep our attention on the osteonal histology. If we go to the edge, we can see these bone lining cells, these purple guys, separating nothingness on this slide from the pink stuff. And here you get a better idea of what these lacunae are, right? So there's less white space in this preparation. You can see there's a nucleus, here's a nucleus, there's a nucleus, nucleus. Each one of these lacunae has a single nucleus, and that's an osteocyte. These are osteocytes encased in a lacuna that happens to be bigger, but again, it's a part of the preparation, not of actual histology. All of these would be about the same. And you get the idea that they're in almost a line with each other, right? So they're going to be one lamella. Lamella are going to be the individual rings. If we zoom out into more developed bone, this is going to be trabecular bone, you can see that the pink stuff is the osteoid. Remember, it's been decalcified, so there's no bony matrix. It's just the proteinaceous stuff that's left behind, the lacunae, the single nuclei in it, and all around them, wherever bone isn't, bone marrow is. All these are erythropoietic cells and some adipose. This is a really high magnification zoom, and again, I don't want you to be worried about what type of stain it is. I just want you to use it to identify some stuff. This is the osteonal canal in the center. And then there's going to be concentric rings of osteocytes called lamellae. Each lamellae is an interconnected ring of osteocytes. And this slide shows the lateral projections within a lamella really well. You can also see some projections from one lamella to the next, but we're going to show you a better view of that in the next slide. This is an osteocyte, this is an osteocyte, this is an osteocyte, this is an osteocyte. And each concentric ring is attached to each other, and each concentric ring is going to lay down its osteoid and then ossify it at the same time. Here you can see again in the center, this is the osteonal canal, or the osteonal artery would be. The bone lining cell is not visible here, they would be on the inside of this ring. And here you can see all the osteocytes. And again, you get that sense that there are concentric rings of osteocytes that are all connected to each other, but here the canaliculi are connecting one lamellae to the next. So you can see that this osteocyte sort of reaches down to the next one. And the idea of that is the outermost lamellae, the one that's furthest away from the osteonal artery, is going to receive its nutrients by means of gap junctions. The bone lining cell, the endosteal cell, is going to remain connected to the first ring of osteocytes via canaliculi, gap junctions. that will then project to the next layer, to the next layer, and to the next layer. So there's a continuous connection both laterally within the lamellae and from the artery up to the most outside ring. Osteocytes connected together, feeding each other's nutrients. This vision is a little bit blurry, but again, we're in a developing bone. Up here is mesenchymal stromal cells, nothing you really recognize. But what you're being shown here is this guy and these guys, right? There's this pink blob with a bunch of purple dots in them. Bunch of purple dots because they're multinucleated cells. These are osteoclasts. Osteoclasts clear bone, and here you have that pink stuff, that osteoid material with lacunae with nuclei in them. If we get really zoomed in, you can see that this is not lamellar bone, it does not have lamellae. It's really zoomed in, so there's only a few lacunae and a few osteocytes. And here you get a really good view of this osteoclast, multinucleated, clearing out this bone. And again, around it is mesenchymal stromal cells. All right, and the last bit of normal bone we have to cover is mineralization. We're going to begin with healthy adult bone. We'll talk about the development of bone and the growth of bone in the next lesson. Osteoclasts clear bone, osteoblasts build bone. Osteoclasts are going to clear out the cylindrical shape of the osteon. It's about 2 centimeters long, 0.2 centimeter radius. They clear out a hollow tube. Into that hollow tube grows blood vessels. And osteoblasts are going to start on the outside of that osteon canal. And a single layer of cells are all going to release a proteinaceous material called osteoid. That's going to push the cell that's making it away from the edge of the cylinder, and the cells that are near it away from the osteoblast. The osteoblast will then be surrounded in its own osteoid. And all of the cells in that lamella do the same thing. All of the cells of that lamella have oriented their osteoid in the same way, and they'll all ossify at the same time. Once ossified, a next lamella does the same thing. When they first release the proteins into the extracellular matrix, the osteoblasts are releasing a compound called osteoid. Osteoid is organic. Organic means not mineral. That means proteins. The thing that gives bone its tensile strength, its ability to support weight, isn't how hard it is. It has to do with the arrangement of the type 1 collagen, the primary protein of osteoid. Each subsequent lamella orients their type 1 collagen fibers in alternating directions to give tensile strength. In that osteoid is also many other proteins, the names of which you do not have to know, except for osteocalcin, a protein which helps hold on to calcium and phosphate. You already know calcium and phosphate are stored in bone. Calcium and phosphate are stored as a crystallized form called hydroxyapatite. You do not have to know the formula, but I just want to show you what it is. 10 calciums, 6 phosphates, 2 hydroxyls. Now, medicine is a soft science, right? Biology. So you're probably not familiar with the concept of nucleation and crystallization. Ask an organic chemist, and that's what happens in the lab every day. Once a crystal starts to form, it feeds forward and continues to crystallize, which is why the lamella must release osteoid and ossify at the same time, because their osteoids are going to be continuous with each other. And so when they release their matrix vesicles, the whole thing is going to crystallize at once, and then the next row gets going with their type 1 collagen in alternating directions. To crystallize, you need a lot of the stuff that's going to be in the crystal. So osteoblasts secrete their osteoid, and they become called osteocytes when encased in bony matrix. Osteoid becomes bony matrix. Osteoblasts are going to generate calcium and phosphate nearby to them. Osteoblasts do that with an enzyme called alkaline phosphatase. Kinases add phosphates to proteins. Phosphatases remove phosphates from proteins.